Okay, so let us start then. We are discussing particularly the reactions of pyridine, and we have completed the reaction related to pyridine based on electrophilic as well as nucleophilic reactions, more or less. Today's class will be the concluding class on pyridine reactivity, which will be including uh, the miscellaneous part of the pyridine reactivity. Particularly, we'll be discussing the chemistry of uh, hydroxypyridine. We'll be discussing the photochemistry of pyridine compounds. Also, we'll try to give touch on the pyridine N-oxide chemistry, as well as the reduction chemistry on pyridine derivatives. Okay, so quite a lot of things we'll be looking at, mostly the reactions. So you have to be uh, going through properly so that you can understand the slight differences in various parts of the reactions. Okay. So we'll start with the hydroxypyridine then. Now, hydroxypyridine, when we talk about, definitely it is the hydroxy group which has to be installed in the pyridine, and you have already three positions. You have alpha, beta, and gamma position. So there are monohydroxypyridine. You will expect as three types of monohydroxypyridines. Now, this is the alpha one, where you have the nitrogen, and just the alpha position you have the hydroxy group. Okay. Now, if you look at what I have given here, you have the equilibrium between these two structures. Okay, these two structures. So you have OH. So here you can have proton transfer. Okay, so that can happen to have this particular structure. Now, you why actually it happens? Definitely, it is the alpha position. So you have the enolization. I mean the tautomerization will be feasible. And if you look at the pKa of this particular oxygen, what we find is it is very, very low, right? So that means the proton, if you attach here, that proton will be very acidic, okay? And which in turns, I mean, it indicates that this OH, this hydrogen is highly acidic. Okay, so that's why it will prefer to have this structure. Okay, and ultimately you can write this structure as in this form. So this is the deuterionic form. Okay, so what we can tell is that 2-hydroxypyridine or the alpha hydroxypyridine, it stays in this deuterionic form. Okay, and the major since you have this is acidic in nature, so the major form will be between these two. Your equilibrium will be shifted towards this side. Okay, so you have more percentage of this structure and less percentage of this. Okay, so this is less, this is more. Okay, now similar situation we will also expect from the 4-hydroxypyridine. Okay, you have again the conjugations, you have the probabilities of electron cloud movement, and you have the structure. And here also, if you look at the pKa, pKh, what you will find is as 3.3. Okay, so it is also quite acidic, and you will have the deuterionic form here too. Okay, so you have deuterionic form here, similar to the alpha. So you have gamma hydroxypyridine will also stays in this deuterionic form, or you can tell like these two form is equilibrium, and you have more percentage of this one. This is more, okay, and this will be less, okay, less percentage. Now, what will be the situation for beta hydroxy? Now, beta hydroxy, we also see the deuterionic form, but remember here what we find, the pKa of this one is close to 5.2. What we see in case of what we see is in case of beta hydroxypyridine, the pKa of the NH is close to the pK, I mean the similar to the pKa of just the biapyridine. Okay, so biapyridine also have 5.2. Okay, so what we can understand from here is that this uh, compound, okay, if you do protonation, the protonation will take place at the nitrogen. Okay, like if you have just at the H plus. Okay, so what you see is that this lone pair will be taking that one, and the pK is not that much. It's not that much basic, so it will behave almost similar to the pyridine. Okay. Now the deuterionic form, what we'll see is that if you do the pi cloud movement, we'll find the different structure, and among these different structures, one of the prominent structure will be this one, where you see a positive charge will be the alpha to nitrogen, and a negative charge will be alpha to nitrogen. Okay, if you just keep on moving the pi cloud. Okay, so from here, how it is forming here, you just need to this is positive charge on nitrogen, so you can just make it neutral, so your positive charge will be at this situation. So you'll have this one. Now, why I'm telling this one, this is very, very important, because you see the word written here, 1,3 dipole. So you have 1, 2, 3. So this is 1,3 dipole. That means it can do 3 plus 2 cycloaddition reaction. What it can have 3 plus 2 cycloaddition reaction. So this is important in that case. Okay, so you'll see the examples based on that. Now your job is to make hydroxypyridine from pyridine itself. Okay, so from pyridine, how you will make the hydroxypyridine? Okay, I'll give one small clue. You can go via nitration or halogenation. Okay, or halogenation will be one of the intermediate route you can think of, and then you can do nucleophilic substitution reaction to make this one. So this you will try in your home assignment to develop the synthesis of 3 hydroxy, like 1, 2, 3 alpha beta gamma hydroxypyridine from pyridine itself. Okay. Now we'll move to the reactivity of hydroxypyridines. So if you look at here, I have written 3 of the form, the alpha and gamma. I have written in the ketonic form, because that form will be the prominating form. Okay, it will be in the prominating structure, and the beta I have written the normal hydroxy one. Okay. Now if you look at if you give the electrophile, what you see is that for alpha, you can have the installation of electrophile at this center or this center. Okay, so that is being guided by the electron cloud movement. Okay, so similarly, if you look at for the beta, what you see is that your electron pi cloud movement will be this way. Okay, so C-centered reaction will have these two positions. Okay, these two positions, the electrophile can be attached for the beta hydroxypyridine. Whereas the gamma, we will see it will be the beta position. Okay, so in this case, like alpha hydroxy, the gamma hydroxy will be doing the reaction in this direction, similar to you'll see in this direction. Okay, this direction. So based on that, we'll see the reactivity. Now, suppose you are having this ketonic form hydroxypyridine. So this one, if you treat with the chlorine water, it is very reactive. So what we see is that the beta position, okay, it has been fluorinated. So that is one of the reaction. Suppose you are having the gamma hydroxy, what you'll see the beta position reactivity. Here also we see the nitration reaction you can have in this section. Now they look at the yield. Okay, its yield is quite low, and definitely you have the protonic source, right? You have H plus, so H plus will definitely diminish the reactivity. Okay, you can have the nitrogen, can get the protonation, and you can have the ring will be deactivated, and the reaction will be slower. So your yield will not be good, but if the product is happening and product is forming, you will have the product formation at this place. Now here you see, you don't see the dinitration. Okay, definitely you can see the mononitration is giving so low yield. If you go further now, if you have already installed one electron withdrawing group, so that means the ring became very deactivated. So the second nitration is very difficult. Okay, so you don't see generally the second nitration. Now when you take the beta hydroxypyridine, you can see the Manichi reaction. So you're having the formaldehyde and secondary amine. What you see is the reaction will be taking place at this center. Okay, so reaction is taking place at this center. It can also happen at this center if you give excess reagent and if you do prolonged reaction, if you increase the reaction time. So here the yield is quite good. You can easily see here because you don't have the deactivation at this situation. Okay, so your reaction is quite nicely proceeding. Now another reaction is you have the sodium iodide people are using to do the iodination. So your iodination is happening here. Here also the yield is very good. Okay. I'll ask one question here. What type of reaction this one? Can anybody tell this iodination reaction? It is nucleophilic or electrophilic reaction in this case? Can anybody guess from the reaction conditions? Anyone want to give the answer? What type of reaction it is? It is nucleophilic or electrophilic reaction? Nucleophilic? Okay, so tell me the job of sodium hypochlorite, NaOCl. What is the job of NaOCl here? Do the reaction proceed if we don't give sodium hypochlorite? Or any other alternative you can think here? If I don't put sodium hypochlorite, what could be the alternative reagent here I can use? Can anybody suggest?
Sir, is it forming I plus?
Yeah, so actually it is initially forming the iodine. So this is the reaction is you have the oxidation, iodine is generated, and from the iodine you have the reaction. So it is the electrophilic reaction. So you have E plus
I plus.
Yes. So that is the main thing here. Okay, so oxidation happening. The job of this hypochlorite is to do oxidation to generate the iodine from iodide. Okay, and then iodine is reacting. Okay, now iodine is reacting in the sense of I plus. Okay, so iodine is very good. You can do iodination. So you have this one, right? 2I, and one of the I is acting as the electrophile. So this is going to come out. Okay, so your reaction is happening this way. So this is the thing what I am actually telling. Here you can replace the hypochlorite with some other oxidizing reagent, and even use the hydrogen peroxide. Okay, but the problem here, you have the N oxide formation will be there. Okay, so that I mean, better to choose some other kind of oxidizing reagent which can easily do oxidation, but doesn't actually do oxidation to the N center. Okay, so that's why I think people have utilized this one, hypochlorite, one of the cheapest oxidant. Now, let us look at another interesting reaction, which is very, very important in terms of exam. Okay. Here you look at the alpha position keto form, okay, hydroxy compound. If it is treated with POCl3, what could be your product? Okay, what could be your product? Now you remember when you are having the phosphorus kind of reagent, okay, POCl3, always remember one thing. This has the philicity towards oxygen. So what it will do is it will try to get attached to the oxygen, okay, and that happens. So you have nitrogen here. What is happening? It is falling here, and now this is attacking, okay, and you have one Cl is coming out. So that is Cl minus. Now you have nitrogen plus. So what can happen? Cl minus can attack here, and you have neutralization. And after that, what you see, this nitrogen carbon single bond can become a double bond, and the whole this phosphorus part can come out. So you can have the P double bond O formation, and that will be ending up with the chlorination at the two center. Okay, so you know, right? The from hydroxy from suppose you have nitrogen here from uh, halogen. Suppose you have halogen at the alpha, beta, or gamma position in nucleophilic reaction. Suppose you are having KOH, okay, and you are having some suitable solvent and heating it, reflexing it. What it will do? So the O minus is going to attack, and you are displacing the halo, right? So you are making the hydroxy from the halo, right? And it is just the reverse reaction. Understood? So you are having the hydroxy. Now you are treating with some halo source, and you are ended up with the halo compound. But so it's very, very important in terms of exam. Another reaction you have this compound. Now this compound, if you look at this, this is the structure. It can behave as the diene in diol reaction, right? Now in diene reactivity, what you find is that if you use the dienophile, suitable dienophile, what you see is that the product formation. So you have 4+2 cycloaddition. Okay, so you'll have this product. So remember, it's a complicated structure. It looks. What you can do is you can just like do like this. You can place the molecule like this way. Okay, and you can imagine like this. So you have, this is your molecule, dienophile. So it is reacting like this. Okay, this center, now this center is attacking here, it is going here. Okay, so after that you can reorganize and rearrange, and you will see the endo product. Okay, I think the diol reaction, Parimshar is already teaching you. So you will understand how the endo and how, when will be the exo and when will be endo product. Okay, So here you will see the endo will be the major one, and this will be the actual orientation of the product. Okay. What we see if you have another, suppose, dienophile, so you can have the similar type of reactions, and you will have this as your product. Okay. Just you need to do 4+2 cycloaddition, and you will have the product formation like this. Now here, if you look at, since you have a double bond here, so this here we don't think about endo or exo, because you have these two and these two will be expecting on the same plane, because you have a double bond here. If you don't have double bond, suppose here you are using the just alkene instead of alkyne, then you have to think about the endo or exo. Okay, and that will be based on what group you have here. So here you take one home task. So the home task will be this is so. Suppose you are having this compound, you are treating with this reagent, so you have to find A, and then you are having this reagent and heating it, you have to find B. So what could be your A and B? Okay, that you have to find. So this is you take as the home task. So you have two home tasks. One is the synthesis of hydroxypyridines from pyridine, and you have this reaction. Now we look at the photochemical reaction. So photochemical reaction is one of the important aspects we should study regarding the pyridine. Now here, if you look at the pyridine, pyridine is not like benzene, right? So that means your pi cloud is there, this aromatic, but it's not evenly organized. So your pi cloud has some unequal distributions, right? Due to the presence of N. So what we see is that in pyridine, these two double bonds, okay, these two double bonds, they behave differently than this double bond. Okay, so these two is behaving differently than this double bond, imine double bond. Okay. Now what we see is that if you irradiate under UV light, okay, so below 300, so generally 254 nanometer, what we see is that pyridine undergoes 2+2 cycloaddition. You know the photochemical reaction, 2+2 cycloaddition is allowed, right? So what we see is these two pi bonds, they undergo 2+2 cycloaddition reaction like this way. Okay, so you'll have this arrangement that we see, and its half-life is very less, so you have only 2 minutes. But that means this compound is very, very reactive, so it can quickly react. And if you have suppose sodium borohydride, what it will do, it will quickly reduce this one. The imine can easily be reduced with the hydride transfer process. So if you use the borohydride, so it will quickly react, and it will make the amine. Okay, so your now the stress will be a bit less, and it will be a bit stable, so can be isolated. Now another thing is that so this compound is very unstable. So if you carry on the photoreactions, what ultimately will be the situation is you have the ring opening. Okay, so first thing is that this imine bond, this is very prone to get hydrolysis. So what it will do in presence of water, this will be like this, right? Hydrolysis will have, I mean, not the amine, it will undergo cleavage. So imine will be cleaved, right? So you have a NH. So you can think like this way. What I can write here is like this. So you have, this is already double bond. I'm not writing the hydrogen here. What you can see, the imine hydrolysis will be ultimately it will give. So this will not be there. You have NH2, okay, and you have, this is C double bond. So that means you have CHO. Okay, so already one hydrogen is here, right? So okay, let me write in a more nice way. So this is aldehyde, you will expect. and here you'll have NH2. Okay, so this is aldehyde, this is NH. Now what you'll do, in presence of light, it will undergo ring opening under photochemistry. Okay, so this will open the ring. We have this form. So that is there. You have NH2, we have C double. So you have here you'll have a double bond, here a double bond. So ultimately you will have this structure, right? So you have a double bond. You have NH2, and you have CHO. Okay, and this is the structure. So what we see is that that can happen. Okay, so that product has been isolated and characterized. Now, suppose you have this the 2-hydroxypyridine type compound. Now, this compound, uh, if you do photolysis, what is going to happen? Okay, so we are now moving to the hydroxy system. Okay, so N is protected. You have methyl here. Now this 2-on system, here 2 double bond. So what we see is that this compound will undergo uh, unimolecular uh, cyclization. Okay, so 2 plus 2 photochemical reaction cyclization. So you have this reaction. Okay, and that will give you the site amide formation, and you have this pro-member ring formation. Now, interestingly, if you just change the solvent from ether to water, what you see is that the different, okay, yeah. So what you see is that you'll see a different chemistry. Okay. Now here what you see is that bimolecular reaction. So two molecules, so two of them, they will react. Here what you will see is that a intra photochemical reaction 2 plus 2 cycloaddition. Okay, so here you see the inter-reaction. So two of the molecules we find is that they react. So 4 plus 4 cycloaddition reaction. You can think like this one, and another molecule is approaching and in the opposite direction. Okay, so in one case, you have the N-Me double bond. This is the downside. You have N-Me double bond, the upside. Okay, and initially you can think like this way. Let me give you the initial situation. So here you have the N, okay, part, and double bond you have here, this double bond, okay, this NME. Now your double bond was like this two double bond, okay, this two double bond was like this. Another molecule, it will come just the opposite way, okay, so that will come like this way. Got it? Here you have the double bond, here you have the NME, and you have double bond O. Got it? Now your reaction is happening these two and these two. So you have the reaction. Suppose here this is moving here. Now this is attacking. So in this way you have the formation. Okay, so 4 plus 4. This is 2 plus 2 cycloaddition photochemical. This is 4 plus 4. So 4 plus 4 is also allowed. 2 plus 2 is also allowed. Remember, photochemical 4 plus 2 or 4 plus 6, they are not allowed. Okay, but 2 plus 2 or 4 plus 4 is allowed. So you will have this as your product. Now, suppose you have this dibromo benzylic compound. Now, this compound, if you treat with this particular heterocycle, so what you see is that in presence of base, so this base can abstract this proton. You have an anion here, and that anion is stabilized. Okay, so that anion can act as the nucleophile, so it will attack here. Similar, two equivalent will make two of these nucleophilic reaction, and you will have this product. Okay, this product. So let me erase this one. So you'll have this as your product. Okay. Now this product, interestingly, if you do photolysis, what we see is that this product generates this as your molecule. Okay, what happens here is that you have this bond and this bond, they are close to each other, so they will undergo 2+2 cycloaddition reaction. Okay, got it? So you have 2+2 cycloaddition reaction, and you'll have this product. Now remember this 4-membered ring formation in between the 2 6-membered ring. So it is a stress. I mean, this compound is not so much stable. What happens? It undergoes ring opening reaction under visible light. Okay. So if you make this one, you have to preserve it in the dark. Otherwise, if you keep it open, what will happen is that this again go back. Okay. So we have a ring opening reaction under photochemical condition. So this type of different chemistry we see for pyridine derivatives. Okay, so other important reactions, let us look at. Suppose you have the methyl at the 4 position. Now this methyl hydrogen is acidic. Okay, so this negative charge, it will be stabilized, right? And you can have a negative charge on nitrogen after delocalization of the electron cloud. That means this negative charge is stabilized, so this hydrogen is acidic, and based on that, you can have reaction 2. So suppose you are having this as your compound, you are treating with methyl iodide. So methyl iodide will first, it will be attached with the nitrogen, so you have the N plus. Now, if you treat with one electrophile like PHCHO, aldehyde, benzaldehyde, what we see is that the reaction will take place at this carbon center, because this carbon having hydrogen which is acidic. Okay, so what we see is that it will form this structure, and then you have the nucleophilic attack on this carbon, and that will be giving you this O will be converted to OH, and then you have another hydrogen here. So finally, water molecule will be coming out, and you have this double bond formation. So what we see is that kind of aldol type of reactions we will find. Okay, so this is one of the aspects. Another important part is that suppose you have, this is your compound, you are having acetate, acetic anhydride, and you are adding the benzaldehyde. So acetic anhydride, so what it will do, you have the first acetylation at the nitrogen center, you have positive charge, you have the similar type of reactions. So sir, আমি একটু ক্লাস নিচ্ছি স্যার। Okay, so we are discussing the reactivity of 4-methyl pyridine. Now, what we see is that if you treat this compound in presence of benzaldehyde and acetic anhydride under acidic condition, what we see is that first the acetylation will take place at the center. So you have acetic anhydride. I think all of you should be able to make the mechanism. So what we see is that you have nitrogen lone pair, so that will be attacking here, and finally this will come out. So you have acetylation. Okay, and you have a positive charge, so it will be as usual. This hydrogen is acidic, so it will make this neutral compound. Now this neutral compound can act as good electrophile. I mean, it can attack the nucleophile. Sorry, it can react with the electrophile, act as the good nucleophile. And here, if you see the benzaldehyde, it is acting as the electrophile, right? So the reaction will be happening in the same way. Now you have acetate here, so that can be cleave out under protonic condition. Okay, so what we see is that this will be protected. So in this way, under acidic anhydride mediated reaction, what we will see is that, like here you see the methyl is still at the end, right? And you cannot, demethylation is not so easy. But the major part here is that you can utilize the acidic anhydride and you can end up with uh, the alkene formation at this carbon center. Okay, so similar aldol type of reaction. Now, another reaction is, suppose you have this as your compound, you are treating with very strong base like secondary butyl lithium. So what it will do at very low temperature, as I told, it will prefer to act as base rather than nucleophile. So here you see the -78 degree temperature. So it will act as base and deprotonate this methyl and the ammonia NH2, and it will have these two lithiation. Okay. Now these two center, they both can react as nucleophile, and this carbon center will be better nucleophile than the nitrogen. So what if you have some kind of ester, okay, so the carbon center, it can attack and OET will be coming out. You will have the keto formation, and then NH can react with the keto, okay, and to get the imine type of compound. Okay, so you'll have finally this will be your product. So what you do is that you practice the mechanism how this is happening. So initially the imine will be there, and then you have the benzylic hydrogen, so you'll have the tautomerization. So you'll have finally this will be your product. So initial product, I think everybody has got. Your double bond will be here, and there will be no double bond, but that will be rearranged to have more stable compound. Okay, so this one. So these are few reactions. Now we'll look at the reactions similar to like the alpha methyl system. So this is alpha methyl is also having the hydrogen, which is acidic. If it is the methyl group is at the alpha to the pyridine. Now you have the similar situation we have seen in the 4-methyl case. Now similar type of reactions you can expect. Some examples here. What you see is, suppose you are having using the amide base. Okay, so amide base, it will definitely abstract the proton here first. So always remember, if you have a chance of abstracting proton, that will be your first choice. Okay, you know already in the amide cases, if you use the amide and liquid nitrogen, liquid ammonia, you have seen the Chichi-Babin reaction. So amidation at the alpha to the nitrogen, okay, of the pyridine derivative or pyridine compound. But here you see you have this CH3, which is basic. I mean, the proton you can easily, the proton can easily be abstracted. So it will abstract the proton, it will generate a negative charge, and then you have the reaction. So here, if you look at another non-protonic nitrating reagent, okay, so propane, nitropropane, that can be utilized. So this negative charge can attack on this nitrogen, and you have the nitration. Oh, thank you, sir. So you have the nitration here. Okay. This way you can have non-protonic mediated nitration reaction. Okay. Now these are the things I am showing you so that you know the different types of nitrating reagent. Okay, so you have seen already the mixed acid, you have seen the N3 5, right, NH3 and NO2. So that system, combined system. You have seen now the nitropropane. Okay, so these are the different reagents people are using. Similarly, here, if you look at here, the N-butyl lithium is utilized at low temperature, so it will be acting as a base. So it will abstract the proton, and now you have amide here. So what it will do, it will attack the carbon and NMe2 will come out as the living group. So NHMe2 will be the actual neutral compound. So you have the installation of carbonyl functionality at this center. Okay. Another reaction you have, suppose you are using the LDA. Okay. So what it will do, LDA can abstract the proton from here, and you are using the TMS chloride, so you can do the silylation at this carbon center. Okay. And this silylation is quite good. Actually, you can isolate and you can do the mild. I mean, the isolation of anion is not so much easy, organic anion, but you can represent like silylation you can do, and that center can act as still the nucleophile. Okay. And if you have suitable substrate, another substrate, so suppose you have C6H10O, that means cyclohexanone. Okay, so you have cyclohexanone. So what it will do, this will react with the carbon-carbon center, and finally you have water elimination, so you'll have a double bond. Okay, so this is kind of Mukaiyama aldol condensation, what you have learned in your previous lessons. So that type of reaction you can expect here. Now, another type of reaction, suppose you have bromine here at the center, alpha to the nitrogen. Now, you can install the carboxylic acid group here. Can anybody tell what could be the suitable reagent? If I want to make the carboxylic functionality from this bromo, how I should do the reaction? Can anybody quickly tell what should be your suitable reagent? Quickly. Anybody quickly can suggest what is that reaction? It's a very unique reaction. Nobody? This though you should tell. This is a Grignard reaction. Okay, so you have RBr and you are installing the RCOOH, right? I mean, you are doing carboxylation. So what you have to do is you have to just use the magnesium, okay, ether, to generate the Grignard reagent first. So this one, if you treat with magnesium ether, so your Grignard reagent will be generated. So this pyridine MgBr will be generated. And then what you do reaction with the carbon dioxide, followed by you just do water treatment. So carbon dioxide, this will attack and you will have the carboxylate, and then in presence of water, it will be protonated. So you will have the carboxylic acid formation. Now, if you look at this carboxylic acid at the alpha to the nitrogen, right? So what it will do, this is acidic, so you have deuterionic formation. So this proton will be preferring to stay on nitrogen, and you'll have this deuterion. Now this deuterion, you look at this one. Let me tell you, let me remove. Okay, so if the proton is transferred at the nitrogen, you have the N plus, and this is negative. Now this negative, it can come out as the carbon dioxide, and you can have a negative charge here, and this particular part can act as nucleophile. Understood? So that means if you do the carboxylation at the alpha to pyridine, the pyridine can act as nucleophile and can do electrophilic reaction at the alpha position. Well, so after decarboxylation, and then now the regular decarboxylation will not happen. What you have to do, you have to the room temperature decarboxylation you will not find. What you have to do, you have to heat it to decarboxylate. Okay, so if you add the electrophile and heat it, so you have E installation at the alpha to nitrogen. Okay, and that we see. Suppose you have the benzaldehyde and you're heating it at 140 degrees centigrade temperature. What you see is that the pyridine alpha position is reacting to the carbonyl carbon, and you have hydroxy group here. Okay, the regular nucleophilic attack to the carbonyl carbon center. So this type of reactions you will observe. Important part here is that alpha position you have the carboxylic acid group. Another reaction you have, suppose the alkene at the alpha 2 pyridine. Okay, what we'll see is that this center, like if you can imagine like what this particular part can behave. This double bond end, you can think like this electron withdrawing group, okay, more electronegative atom. That means it can behave like alpha beta unsaturated, okay, carbonyl type, okay. So that means it can undergo Michael reaction, 1,4 addition reaction. Got it? That is the point. So if you react with suitable compound, say suppose here malonic ester, so diethyl ester of malonic acid, what you see in presence of base, so this will be deprotonated and it will attack here, and you have 1,4 addition. So you have just the malonate will be joined here. So you will have this as your product. So this is we call 1,4 addition type of reactions, the Michael type of reaction. Okay. So these are different varieties of reactions we see in pyridine derivatives. Okay. Now let us come to quickly the pyridine N oxide. Now if you look at pyridine N oxide, you have O minus N plus, so that means you have more dipole moment towards this direction. Okay. And this compound can have multiple resonating structure. Okay. Interestingly, the same center can be positive, can be negative too. Okay, like here if you look at, you have N positive. Okay, so what you can think is that you can have this orientation. So if it is plain, okay, like this, so this center is becoming negative. Okay, now you can have the same center can be positive. Okay, and that's why you have the complex behavior of pyridine N oxide. Okay. Now let us look at some of the reactions. So electrophilic addition and substitution reaction. Now pyridine N oxide, if you treat with this compound, look at, this is a compound you can do ethylation. Okay, so you have the O minus can attack this triethyl oxide, right? BF4 minus. So your oxygen will be ethylated. Okay, so OET, and this N will be positive, and you have this salt formation. Now suppose you have methyl here, these two center. Okay, this is the meta position with respect to nitrogen, or the beta position. Okay, now if the methyl is here, what we see is that the major reaction will be at the gamma position. Okay, if you treat with bromine with suitable Lewis acid, so you have the Br plus will be incorporated here. So that means your reaction will be taking place at the center. So how the reaction will be happening? It is simple. So you have this one, and you will attack the Br plus. Okay, and then you have hydrogen here, then re-aromatization. So it will come back and it will generate the N oxide again. So this way you have the Br plus at that center. Now, if you treat with mixed acid, you can do nitration at the center too, okay, at elevated temperature. But the yield is not too high in these cases, okay, because you have the O minus to some extent will be protected, okay. It can do coordination with this, it can bind the thallium here, okay, replace one OSE, so the nucleophilicity will be diminishing. Similarly, it can do protonation here in presence of acid, and nucleophilicity will be diminishing of this pyridine N oxide. Now, pyridine N oxide in presence of bromine and oleum, if you don't have the methyl at this beta position, or beta position if it is open, what you will see is that it will prefer to do bromination or sulfonation at the beta position rather than the gamma position. Okay. Now here what happens, the oleum, in presence of oleum, this will be protonated, and if it is protonated, what will happen, your N is positive. Now this will behave as pyridinium. Okay, and you have learned for pyridinium system, the beta position reactivity is the major reactivity for the case of electrophilic substitution reaction, and that has happened here. If you use non-protonatic medium, then it will prefer to go for the gamma position. Okay. Now another type of reaction, the addition of nucleophiles and loss of oxide. So that will be N oxide will be removed. Now this is pyridine N oxide. You're using nitrating reagents. So you have nitration here. Remember, you don't have methyl here, so your reactivity is diminishing. Yield is quite low, 48%. Okay, and now your ring is highly deactivated. So if you use the methoxide will displace the nitro. So it will attack because ring is highly deactivated. So if we call this reaction as the ipso attack, I think you have heard that one. Okay, so ipso chemistry here, nitro will be coming out. You have the OMe installation, and now if you treat with the anhydride, acetic anhydride, so this will be acetate, so OAC, and OAC will have, so another OAC will be there. Okay, so you have like this is, you have O here. So this is attacking. Okay, so this is coming out. That means here acylation, and you have another thing is ACO minus. So that ACO minus will be attacking at this carbon. So you'll have two OAC, right? And then this will undergo acetic acid liberation process and to generate the aromatic compound. So pyridine will be coming back, and you have the acetic acid is the forming. Okay, so this you will see in the medium. Now, since you have, if you do the water treatment, this will further undergo hydrolysis, and it will generate the hydroxy, and 2-hydroxy will be actually in the form of keto. Okay, so this will be your major more concentration instead of hydroxy. Okay. Now, suppose you have this as your compound and you're treating with acetic anhydride. Okay, what will happen? As usual, you have acetic, O will be acetylated, and you have OAC. Now OAC is going to, this is the alpha position, remember, alpha position methyl. So it will be, instead of attacking at this center, you have the acid-base chemistry. So you have negative charge generation here, and you have this double bond formation. So in negative charge, that will fall here, it will neutralize, so you have double bond formation. Now you have cyclic cyclo addition type of chemistry, and this will move here, it will move, and this will be the oxygen will be coming out from the nitrogen. Okay, so oxidation, you can tell about this in terms of nitrogen center. So ultimately, this will be doing acetylation at this carbon center. So this carbon center will be acetylated, and this oxide will be removed. So you have finally, this will be your final compound. Now, just pyridine N oxide, if you treat with the POCl3, what will happen is that first this will be reacting, so POCl3. Now Cl minus will be coming out, and that can act as the nucleophile, so it will be reacting. So plus Cl minus. Okay. Remember here your POCl3. So if it is attacking one, Cl will be coming out as Cl minus. So that Cl minus can attack here to generate this compound. Okay. Now this can quickly undergo aromatization. Okay, because the phosphorus is having the filicity towards oxygen. Phosphorus will try to have complete hold on the oxygen. Okay, so what will happen? This will easily undergo aromatization, and will have the fluorination at the center. Okay, so alpha to the pyridinium N oxide. Now, if you treat the pyridine N oxide with the Grignard reagent, so phenyl magnesium bromide, so this nucleophile pH, it will attack, and O minus, so that MgBr will be there. You will have this one. Now, what happens is that you have ring opening, okay, and in presence of acidic anhydride, you have acetylation here, and then ring closing process will take place, and finally you will have the acetic acid will be removed, and which will be giving you the phenylation at the alpha 2, the pyridine. Okay, so this way you can do alkylation or arylation alpha 2 pyridine. Okay, because you know that Friedel-Cap reaction is not possible for pyridine derivatives. So that's why this is one of the route by which you can do alkylation or arylation to the pyridine at alpha position. Now the last one is the reducing reagent reactivity. Quickly, this will be the last slide. So your pyridine definitely is more reactive with respect to benzene. So benzene, if you treat with regular reducing reagent, nothing is going to happen. But pyridine is, since you have the unequal pi cloud distribution, what we see is that in presence of different reagents, reducing reagent, you have the different product formation. For example, if you treat pyridine with simple hydrogen and platinum in presence of acid, at room temperature, it will be completely reduced with excess of hydrogen source to the pyridine. And similar reaction we can also see if you use the excess samarium iodide in presence of water, we have the same reaction. And in presence of other reducing reagent like lithium triethyl borohydride, so that excess if you use, you will have the complete reduction. Okay. The simple sodium borohydride doesn't react with the pyridine, but lithium borohydride, lithium aluminum hydride, not borohydride, lithium aluminum hydride will react with the pyridine, and you have 1,2 reduction. So you have one hydride will be attacking here. So this hydride LAH, that hydride will be attacking at the center, and you have N minus, that center will be connected with the lithium, and then you have if you do the water treatment, if you do the proton source, so you'll be having the 1,2 reduction. But if you treat with the metal and liquid ammonia, okay, like lithium or sodium with liquid ammonia, what we see is that Birch reduction will happen, and that will give you the 1,4-dihydropyridine. Okay, 1,4-dihydropyridine, and that will be governed by the stability of the radical. Okay, and you just go revise your Birch reduction chemistry, you'll understand why the 1,4-dihydropyridine will be formed. Okay, so that will be governed by the stability of the radical. Okay, now suppose you have this as your compound. So alpha position you have this ester, okay, and meta position, beta position you have this ester group. If you do the Birch reduction, in this case, what you will see is that this compound will have the 1,2 reduction. So that means you will have, it will undergo, it will generate first initially this as your NH, okay. This is ester. Here I'm writing R, okay, and this is also ester, writing R. Now this carbon center, you have initial radical, and then you have one sodium that can donate 1 electron, so it will be negative, okay, and that particular negative charge is stabilized because you have ester here, so that negative can be stabilized through the resonance, okay, from this side to this side, and this side also. You have both sides. You have ester here, you have ester here, okay. So what we see is that the stability of this negative charge will give you the formation of negative charge at the center, and now this center can act as nucleophile. So if you give any kind of electrophile, that will be incorporated here. So if you use the methyl hydrides, methylation will take place at the center. So this we see in reduction chemistry and its application. Okay, and the last one is you have, let me make it clear. So if you use this one, okay, ClCOMe, so first the nitrogen will be protected and then you are doing the reduction. So what will happen, the nitrogen, you have the lone pair here, so it will react and it will do this N positive charge to generate the N positive charge species. And now the reduction will be more facile. So now this time borohydride will react. This is neutral one, borohydride is not so much active to react, but this is cation, now it is more electron thrusty. So you have the reduction. Okay, so borohydride will do the reduction. So you'll have this as your product. Now this one you can use as the diene in the diene reaction, and it will do the 4+2 cycloaddition reaction with this diene. Now another is the pyridinium species. So pyridinium is more reactive, so it will undergo the reduction very nicely. If you use the Birch reduction, that is again 1,4 dihydro type of reaction will be happening. If you use the hydrogen platinum at room temperature, you'll have the full reduction. And if you use the borohydride, now the borohydride will do the reduction. So this reaction will be a bit tricky. So first is that this 1,2 reduction will happen. Now you have nitrogen is neutral. Now this you have allylic system with respect to nitrogen. So you can have this bond is falling here. You have the protonation here. Okay, and then you have again the iminium ion cation, and then it can again undergo reduction. So ultimately you will have the final product, this one. Now this one cannot have any iminium now, so your reaction will be stopped here, and you have the one single double bond will be remaining at the center. Okay, so this is all about the reduction chemistry. I just go through here. I have discussed quite a lot of reactions. You have to practice well, and in the next class we'll be moving to the new topic. Okay, so if you have any queries, you just quickly ask if you have any doubt. Otherwise we'll stop here and we'll be meeting you tomorrow again at the morning. So any queries?
Sir,
Yes.
in the slide number 6.
6.
The reaction.
Okay, slide 6, right?
Number 6.
Okay, just let me quickly see. Slide 6. Okay. Yeah, 10. Slide 6.
Reaction with TMSCl, asymmetry.
Yes.
Sir, why this asymmetry not attached with the nitrogen?
No, here you look at which one is more nucleophilic. Okay, so first what you are doing, you are treating with LDA. Okay, so what is the job of LDA? LDA will abstract the proton. Okay, so this you have CH3, so it will be abstracting proton from here, so it will be generating CH2 minus, right? It will be generating CH2 minus, right? Now CH2 minus and N dot. Are you getting? In lone pair. So which one will be more nucleophilic? Suppose you have a carbon negative. Yes. So that's why your silyl will be attached at the center. Did you get the point?
But sir, it can resonate to the nitrogen.
No, it's okay. Resonance can happen. Resonance can happen. But the thing is, which one is more nucleophilic? As soon as it is generating, you have TMS chloride. So you have immediate reaction to the TMS chloride. You're getting? So that way it will happen.
Sir,
Uh,
I was asking,
huh.
in case of aldol for Mukayama aldol type, a nitrogen center react with the same methyl. So that's why I think it's nitrogen should react.
No, in this case, since the nitrogen has nucleophilicity is less than the carbon, the reaction will be driven by the carbon center. Okay. Stability you can explain, since the carbon is negative, it is alpha to the nitrogen, so it will be stable via the resonating structure. Okay. But if you talk about the reactivity, it is the carbon center which is more nucleophilic than the nitrogen. And you are talking the nucleophilic reaction, I mean the electrophilic reaction, you are adding the electrophile, so your reaction will be preferred which center is more nucleophilic based on that. Clear?
Yes.
Yeah.
Yes.
So anything? Okay, you go through. If you yes, tell if you have any queries.
No, sir, I understood.
Oh,
It's
okay,
okay.
okay. So you just go through all the reactions. If you have any queries, any doubt, you can come up later on, and I'll happy to discuss that part. So thank you for attending today's class. You tell your friends to attend the classes, upcoming classes. Okay. So I'm stopping here.
Thank you, sir.
Thank
Thank you, sir.